Hey folks, welcome back to the Combo Class bonus channel. Had a little glitch where it started the stream early, but now we're on for real. And for any future viewers as well, we will talk about some interesting prime number patterns that you may have fun watching. And if anybody tunes into the beginning of this and not later, stay tuned on the main Combo Class channel for a full episode coming out right when I'm done with this stream in about an hour. But to start off today, I figured a good kind of meditative activity that'll also help us problem solve a little bit is to, like the other day, when we found all the prime numbers leading up to 100 by an elimination process using some shortcuts, why don't we look at all the prime numbers there could be in the next range of 100 numbers, in the 100s? And I don't mean all the three-digit numbers. That would be a longer quest. Maybe we'll get good enough at finding good problem-solving techniques we'll be able to speed run all this three-digit primes later. But for now, let's learn some problem-solving techniques and have me share some I've found where we eliminate some primes, but in a slightly harder range. We're not going for the two-digit, one-digit ones anymore. We're going to go for the primes between 100 and 200. Now, it's not just a range I picked because it's kind of natural to us to think we're doubling the amount from before, the next 100, but also because it's a kind of neat range where the primes land. I do know something about the primes on the ends of this, the ones close to 100 and the ones close to 200, that I already wanted to point out in the video. I don't remember any of what all the middle primes are. A few of them would ring a bell, but a lot of them we're just going to have to prove and try and troubleshoot. Now, we can see that of the amount of primes up to 100, there were 25 total. I've added on the one-digit ones on top, and these are the two-digit ones we proved through elimination last time. Now, the next range should contain slightly less, but not too many less than that, because the primes do get sparser, but they're still at a small enough, close enough part of the number line in the 1 to 200 range that we should expect a little less than 25 primes, but not too much less. Now, of course, we could look up a list or train a computer to do this, but that's not fun and that's not going to help us learn problem solving techniques. And in fact, if you wanted to program a computer to do things efficiently, you have to tell it what routes to take and what things to skip, and that takes these problem solving troubleshooting things that we'll try out. Now, first, I was almost going to write down all of the numbers from 1 to 100 and start crossing out, but since that's a little tedious, I only wrote down the ones ending in the 4 digits we know that primes will end in our base. We know that any number ending in a 0, 2, 4, 5, 6, or 8 that's large enough to be in the 1 to 200 range is going to be divisible by 2 or 5 or both. And so we know that we're only looking for numbers that end in 1s, 3s, 7s, and 9s, and these are the ones in that range. Now, we've eliminated it pretty quickly down to having only 40 of the 100 possibilities. So there are 40 prime contenders left here. But we know that not nearly all of these are going to be primes. Now, since we've done the elimination of 2s and 5s, we need to think about what's remaining. Well, a lot of the ones that we need to check off are going to contain one of these one-digit primes somewhere in them, mixed with something else. And so we've already eliminated anything that contains a 2 somewhere in its prime factorization by eliminating all the even digits. And we've eliminated anything with a 5 in its prime factorization by eliminating anything with 0s and 5s at the end. So now in between that, we have our multiples of 3, our three-even numbers. And although those don't have a last digit trait in base 10, and I did write this in base 10 to make it more understandable, although if you want to see some crazier numerical bases, those are the theme of the main channel episode coming out right after this stream. So here in base 10, we can't eliminate the three-evens quite as easily, but it's almost as easy because what we can do is our digit sum game, where three-even numbers in base 10 always have a digit sum that is also three-even. If we add their digits, there's a exact correlation that if the digits don't add to a three-even thing, the number itself isn't. If they do, it is. So to cross out any multiples of 3, we can just go down and kind of meditatively add these digits in our head. 2, 4, 8, 10, 3, 5, 9, 11, 4, 6, 10, that's 12, 5, 7, 11, 13, 6, 8, 12, 14, 7, 9, 13, 15. You can see an interesting pattern here. Do you notice how we seem to get a skipped line, and then a line where the first two are crossed, and then a line where the next two are crossed? Well, that makes sense that it would be periodic at some point, because what we have listed here are basically cycles in mod 10. And although 3 doesn't go into 10 evenly, 3 goes into 30 evenly. So it makes sense that it would cycle after 3 of these cycles. And to see if that pattern holds, we can check this row. If the pattern continues, should have nothing checked off. None of them should be three-even. So, I mean, checked off at this phase. So let's see, 8, 10, 14, and 16. And sure enough, they're not three-even. And now we can be pretty confident it's probably these ones that are the three-even. And in the next row, these ones that are the three-even, and then none there. But just to double check, we can see that's 9. Good thing we crossed it off. 11, 15, 17, 10. There we got 12. 16, 18, 11, 13, 17, and 19. So the pattern continued as we saw. And if we wanted to get more formal, we could prove that that would continue onward. So even if we are stuck in base 10, there could be not too hard of a way to try and cross out every third one without having to digit sum all of them. Once we start getting to bigger number ranges, that would be harder to do digit sums, like ones where we might have to sum the digits twice to start remembering if the number was three-even. Now, we've eliminated everything on this list that has a factor of 2, 3, or 5. And I haven't checked the comments yet. I'll check those in a little bit after a little more investigation here, but feel free to keep leaving them. Now, since we've eliminated those, let's bust out a new term you may not know. There are cool terms for what factors make up numbers, known as the smoothness and roughness of the number. And if we say that a number is some amount, say k, rough, that means that if we prime factorized it, it has no prime factors less than k. All the prime factors are k or greater. So, for example, if we say what numbers are at least 3 rough, well, the even numbers would have a factor of 2, so they wouldn't be. They would only be 2 rough. But the odd numbers, some of those would be 3 rough. And so the roughness of a number can say, what are the prime factors have to be? They're this amount or bigger. And the smoothness is sort of the opposite with the included range where it's this amount or smaller. So if I say a number is like 5 smooth, it means if I prime factorized it, there are no primes bigger than 5 in its prime factorization. And so that does mean I could have tons of 2s, 3s, and 5s. So I can make a really big number that is relatively smooth. For example, a massive power of 2 would still be too smooth because it's has no prime factors bigger than 2. 2 is its largest. So essentially, we've been eliminating certain types of numbers. And now when we look for composites that have still snuck on the list, we're just looking for ones that are 7 rough, essentially, meaning that they have no prime factors under 7. Or no, they have, no prime fact. Well, not quite ones that have, no prime factors under 7. because eliminated all the ones that have prime factors of 2, 3, and 5. So to find that type of number, we could try and use some weird divisibility tricks. There are tricks where you double the last digit, subtract it from the remainder of the number, but that starts getting a little tricky. There's also tricks for 11 where we alternate digits. But instead of trying to use a divisibility trick on a huge batch of these, we can limit the amount that we need to check and just check some numbers by hand by having a much smaller batch we need to check. So let's remember in the last time when we were looking at how can we know we checked off everything on the first list that was a 1 or 2 digit number? Well, we know that 100 square root is 10. So 99 and smaller, they all have square roots here that are smaller than 10. And if we look at what makes up a non-prime number, that means factors multiply into it, and these factors have to come in pairs. And either the closest it could be to not having small factors would be if we have just the square root of the number times itself. But otherwise, we're going to have some smaller factors than the square root because like if it's not a square number, but it's a composite number, we'll have some pairs of factors, and in each pair, one's bigger than the square root and one's smaller to multiply to the number. So here, if we look at what is the square root range of stuff on this page? Well, we're going from about 10 to the square root of 20. Now, what primes that ends up meaning, what are the primes in that range? Because we don't care exactly what the square root of 20 is, but 15's bigger than it, and 13's smaller than it. 14's not, 14 I'm not sure, but it doesn't matter because it's not prime. 13 we know is, and I guess, yeah, it would be 14 point something would be the square root, but in any case, that means 13 is the largest prime, or basically the set of primes leading up to 13. There must be one number from that set as at least one of the prime factors in any composite number in the range we're looking for. Because if we imagine a composite number that has other prime factors because it's composite, but none of them are, how can I phrase it, in the range under the square root or equal to the square root, then what are the other factors paired up with? Anything they'd be paired up with, if it was bigger than the square root together with it, would multiply to too large to be the number itself. And so essentially, if we crossed out all the multiples of 7, 11, and 13 from here next, then we will know that we've covered all of the composites getting checked out. Because once we get to the next smallest number that's composite but doesn't have a prime factor 13 or smaller, that would have to be 17 squared, would be the next smallest, and that's bigger than 200. So now we know we need to just find how to eliminate 7s, 11s, and 13s, but we even have more of a shortcut because we don't need to look for things like 7 times 8, because that's already eliminated when we eliminated the evens. We only have to look for 7, 11, and 13 times other primes, because the other primes will follow the exact same rules and need to be built from something that we've already checked off. And so we need to basically figure out what is the range of primes that 7 might multiply with to make a number between 100 and 200, and same question for 11 and 13. And then we're pretty much good to go. So to figure it out, for 13, for example, to start from the top, what's the range of numbers that 13 can multiply with to, well, no, actually, let's start with the bottom so we can eliminate possibilities simpler. For 7, we can do 7 times 7 as the smallest unseen one yet that didn't involve a 2, 3, or 5. We can also do 7 times the next prime, 11, and we can also do 7 times 13. And once we get up to 7 times 17, that will give us, let's see, we'll need 7 times 17. 7 times 19, where will that get us? That will need to be included. What about 7 times 23? Will that need to be included? That's going to be 140. No, that's too big. 7 times 23 is more than 200. So these are the primes that we're going to need to multiply with 7 to get checked off from the list still, because all the other things that 7 could multiply to in that range had a factor of one of those. Now, how about 11? 11 can multiply to get a number between 100 and 200 by itself. It can multiply by 13. And once we get to 11 times 17, is that too big? No, 17 will fit. And then from there, we will not need to do 11 times 19 because that's going to be too big. That's more than 200. Now, also, I realized we were doing all the 7s, but we already covered some of these. So 7 times 7 was smaller than 100. 7 times 11 is also smaller than 100. Even 7 times 13 is smaller than 100. So we're really just left with 17 and 19 as the ones that will fit in the range to multiply with 7 in the 100 to 200 range. Now, how about 13? Well, we've already covered 13 times 11 with there. So we just need to do 13 times 13. 13 times 17 gets too big. So now let's see. Wait, let me confirm that. 13 times 17, we can think of that as 170 plus 3 17s. And yep, that's too big. So all we need to check off are these 6. Now we need to check what's 7 times these two. Well, 7 times 17 gives us 70 plus 49, which gives us 119. So 119 secretly was not a prime. Now 7 times 19 is going to give us 70 plus 63, that's going to give us 133. So 133, not a prime. And that takes care of the 7 ones. So now we need to look at the 11s. And the 11s were 11 times 11 was 121. 11 times 13 gives us 130 plus 13, 143. 11 times 17, that'll give us 170 plus 17, which gives us 187. So those are gone. And now we just need to take off 13 times 13, and that's going to be 169. And let's see what we're left with. We got a bunch at the beginning, and let's count as we go. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think something's off here, maybe. Something seems off in that sector. There's a chance that somehow one slipped by. Let's think of what that could have been. 7 times 19 we got off, I believe, because those 70 plus 63 is 133. 7 times 23. Oh, maybe we did need 7 times 23, 140 plus 7 times 3 is plus 21 is 161. That's it. 161. I could tell something was looking too close there. 161's not a prime because it turns out to be 7 times 23. So now we're left with how many? 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 21. And I think it looks right, but let's double check. Let me look up how many primes. Well, let me just double check the list just to make sure. So we'll pull up a list of prime numbers and see how we did. And then I want you to also look at what patterns you notice here, because there's some kind of cool patterns in this chunk of primes. Well, according to a list I got here, we should have 101, 103, 107, 109, 113, 127, 131, 137, 139, 149, 151, 157, 163, 167, 173, 179, 181, 191, 193, 197, 199. And yep, this is the list of primes between 100 and 200. And as we get better at speed running them, maybe we'll be able to do all the 3-digit primes real quick sometime. But that's just a fun exercise in problem solving of how to prove to yourself that you've gotten all of the ones in a certain range without having to test everything. Now, what do you notice about this? Well, it's kind of cool how they look like there's so many on those lines. When there's ones on those lines, that's the closest 4 primes can sit, apart from right at the beginning of the number line. Apart from not counting 1-digit primes as being allowed to be part of one, the closest primes can sit is ending on the digits 1, 3, 7, 9 as 4 in a row. It's sort of like 2 twin primes in a row as close as 2 twin primes can hang out. And so those can be called sometimes prime constellations of certain lengths, or this could be called a prime quintuplet along the lines of a prime twin prime. And it's also sometimes called a prime decade because they look like years sometimes. They have to line up with, like, in how a decade would have a 1, 3, 7, and 9 year in it. So we get 2 of those, and there's not that many of those prime quadruplets. We get one in a symmetrical fashion at the beginning and end of this range, which is kind of neat. We also get a kind of symmetrically one where there's one hanging out right at the beginning of the 2-digit numbers, 11, 13, 17, 19. Now, let's look up a list of what are the other prime quintuplets, or as some call them, prime decades. And I think it's interesting in general what sorts of constellations of primes can exist when you talk about different distances that can be. So, wait, I searched prime quintuplet by accident. If I was saying that, I mean prime quadruplet, if I ever said prime quintuplet by accident. So, you got your 5, 7, 11, 13. That one technically fits the bill, even though it's the only tiny one that doesn't have the ending digit pattern. Then you get 11, 13, 17, 19. And then you get these 2, 101, 103, 107, 109, and the stretch in the 190s. And then you don't get another prime quadruplet until 821, 823, 827, 829. Then you don't get another until in the 1400s, in the 1480s. And then the 1870s, and then check this out for all the youngins out there who think that they'll probably be around in like 20 or no, in about 60 or so years. Well, the 2080s are going to be a prime decade. It's going to be 2081 is prime, 2083 is prime, 2087 is prime, 2089 is prime. Oh, cool, a little squirrel. And that's going to be the last prime 4 in a row like that until the 3250s. The year 3251 will start the next one. So we're in time. I'll make sure there's going to be an epic celebration that goes down that day, whether I'm still here or not. Something crazy is going to go down, and not that day, I guess, on those 4 years. And it's going to be such a crazy year that you have to take years off in between. So it's going to be a really crazy 2081, 2082, you cool off. Going to be a really crazy 2083. After those 2, you kind of need 3 years off. And then you get your 2087 and your 2089, and those are going to be pretty wild. So that was just the math portion that I had planned. I'm sure I'll rant about other math stuff, like maybe some more about those smooth and rough numbers. But let me take a peek at the comments first. And as a reminder to anyone who leaves early, check the main channel in about half an hour, because the main combo class channel, not this bonus one, because I'll be putting out a full new episode there right when I'm done streaming. Hello to everyone. Someone asked what nationality I am. I'm basically what you'd call white, but if you want to be specific, I have a good amount of Jewish blood in me and various amounts of types of European, of various different European sorts, um, and a mix of a lot of stuff, but mostly what you would call white. Um, Now, let's see. Now, someone's saying, why don't I do derivatives and integrals on my channel much? Now, here's the thing. I think that calculus often rushes some students into the equations before they get kind of cool gut feelings or geometric senses for them. And so I want to figure out the right way to make some good introductory calculus videos that introduce the concepts in an intuitive way before I start throwing the formulas around. I like to make videos that hopefully not all of them are going to be understood by everyone, but I hope that, like, you know, for different people, they might understand a relatively high portion of my videos, even if they don't know that much math, because I try and pick topics that I've kind of led viewers there to understand in a fundamental way. And sometimes that's just by using numbers and stuff, because everyone's already used those, or shapes or stuff, or puzzles that kind of tap into something you've tried in your mind before. But as we go further, once I feel like I've already introduced you guys to various stuff, we will take things to levels like calculus and onward. Yes, a comment pointed out that 7 times 23 was supposed to be on there. Thanks to Nathaniel Raymond Gentles, who caught that, although I wasn't looking at the comments, unfortunately. Someone saying prime numbers are always around multiples of 6, and it's true that an alternate prime hunting style we could have used is to write down all the numbers instead of just me saving time with writing by writing them this way with just 1s, 3s, 7s, and 9s. If I wrote down all the numbers so that they were lined up with 6 rows, like, but starting at the right point, so I was basically writing rows as mod 6, then I could trim all of the middle ones and just be looking at numbers that are congruent to 1 or 5 in mod 6. So it's true that if we want to do that, that saves the even step and the threeven step, essentially. It's basically the same thing of doing the even cut here and then having to add the digits to trim the threevens, or trimming everything that's not congruent to 1 or 5 in mod 6. So that would be a fun alternate way we might do at some point. Thought this would be more understandable to more people, but you do know I love mod 6. In fact, I show a little bit about base -6 in the upcoming main channel episode. But not saying I necessarily recommend we switch to base -6, but I am saying it has some weird superpowers that might surprise you. Someone's wondering if the pattern of prime numbers onward would be similar. And yes, if we looked at the next range, let's think about what would come next. Well, we would think, okay, if I'm going up from 200 to 300, what's the square root of 300? What's the smallest prime under that? And for each of those primes, what's the range of primes it could multiply with to hit that range? And you kind of go upward as you eliminate possibilities so that you've already eliminated the smaller ones. And so the next range, since we saw there's 21 primes between 100 and 200, and there were 25 primes between 0 and 100, we're going to expect a few less in the next range. I don't know exactly, but I would expect 2 to 4 less primes in the next range than we found here. So maybe not quite that much, but somewhere from 1 to 5 fewer primes I would expect to see on the next list. Although it can surprise you because it's not completely patterned. We know the estimates of how many primes live before a number that we can calculate that approach good accuracy, but on the small number line, they're pretty off because there's more primes than usual in the small number line. So normally if we were doing prime hunting at a big range, if I was saying the primes from 1000 to 1001, there would be a lot fewer than 20 because they do get thinner. In fact, it's very interesting that mathematicians do know about how many primes are before a given large number, but they don't know where they are. So a lot of comments, a lot of them I've already answered in past streams. Another way we could go about this, just to note, is that we could have done some divisibility tricks we might bust out later, because there are things you could use to test if things are divisible by 7 and 11, and that would be a different way to go through and do that. And you can just go through and check off every 7th, but that gets a little more tedious than problem solving. Now, another note is, just since someone noted about calendars when I was talking about the future years, I wonder what year or what month those are going to start in. Because if they're non-leap years and they start in the same month as another non-leap year, the calendar will be the same. So, like for example, let's see what was the last calendar that matched this one, I wonder. Like this year, whatever day started this year, the last year whose calendar started in that day and wasn't a leap year would have the same days on the same spots. So save your calendars, maybe write them in pencils and then you can use them 20 times. And one thing I'll say about calendars is they got a lot wrong, but they got the 12 months right, but that's good. But they got a lot of other stuff wrong. Why does February have too few days? And if the other months are going to have 31s in the mix, why don't you have fewer that have 31 and not make February have so few? Why don't you give a couple of the ones to February? Similarly, there are even better ways of dividing it where, although 12 is cool for practical purposes, the weird fact of the matter is that the year should be divided into 13 months. But I'm going to have to go into that in a longer video. But that actually is the best way to do it. And it seems like I'm going against my protocol of thinking things should be divided with high divisibility. But with the 12 months, you don't get divisible structure within a 12th of 365 and a quarter. So you sometimes need to sacrifice one level of divisibility to gain other levels. Oh, someone has a rotating calendar that rotates and changes. That sounds kind of cool. It sounds like you could make it quite adjustable. So let's think about one or two more fun math things before we jump right into me posting my new episode. Now, this episode is going to be about negative numerical bases. So right now what I'm going to give is a slightly longer version of the quick intro I give in that video to explain the thought process of what we might see there. Now, this is going to be a more detailed version of basically the first minute of the video. But what I want to show you guys is it'll kind of give you a good backdrop for understanding and appreciating the video. So we normally think of if we changed bases by like, okay, we changed the number from 10, but what do we usually really mean? And what usually do we still keep as rules? So if we say we go to base 6, then that means that I'm now making each spot a power of 6. Like there's a 6 to the 0th place is still my 1's place, 6 to the 1th place, 6 to the squared's place and stuff. But that not only do I keep the rule that each power is a power of b, which is 6 in this case, but I also keep the rule that the digits that get their own symbol as a digit range from 0 to 1 under the base number. So in our base, we use a single digit character for 0 through 9, and then there's no digit for 10. It takes 2 digits. So basically, you're going to expect that in a base like this, the number is going to be some integer, and theoretically, you could have non-integer bases, but that is not the topic I went into mostly in this episode, so I'll save all the non-integer base thoughts for another day. Let's assume for now we're going to use an integer so we can try and stick with the rules and just distort the rules a little bit and not have to distort the rules as much. So we're going to have a different integer that it's powers of, and we're going to use digits that are between 0 to 1 under the base, b minus 1. So now let's think about what that makes our range of bases. Well, if here's a number line and 0, we normally think of 2 as kind of the first base, binary, the lowest practical base, and then you go up from there. Why don't we think of base 1 as really practical? Well, some people say it's like tally marks. Now, you'd expect I should like a tally mark system because they're all hyper 11s, and I like hyper 11s in different bases, but in this base, everything's a hyper 11. However, this isn't really what you could call base 1 in the same way. Say it's base 1, you'd have to specify some clarifications, because the rule we made here is that the type of base we're doing, a typical positional numerical base, is going to be an integer number, and we're only going to use digits from 0 to 1 less than that number. So if I picked my number to be base 1, I'm only using the digits 0 to 0. So I'm only using the digit 0, and it doesn't really work from the same rules that if I use higher powers of 1, but add more 0 amounts of them, that I get somewhere. So it really wouldn't follow the same rules to call this tally marks because I'm using the b number. I'm not using 0 to b minus 1. And then I don't really have a symbol for 0 apart from the empty string. So if I end up allowing a 0 and 1s, then we're using like as many digits as base 2, but breaking the rule and not even being functional. So basically, base 1 doesn't really make sense. And we could say it doesn't make sense because it's too close to 0. 1 minus it, as the 0 to 1 minus it, is too small of a range to use for digits. We need a range, not just the 0. So how could we extend this? Well, like I said, one way of extending is to say I'm not going to use an integer. But even if we're forced to use an integer, and I want to use this, how can I just mildly adjust this rule? So we're going to note that what this made us do is our integer is going to be greater or equal to 2. We'll call this integer n. Or we'll call it b. So the base number is greater than or equal to 2. So what if we do this? What if we say 1 didn't work because it's too close to 0? What's further from 0 that's not 2, 3, 4, 5, or whatever? Well, there's numbers further from 0 that way. I don't mean -1, that's going to be too close also. But what about starting at -2? -2 is as far away from 0 as 2 is. Now, you might at first think this means that we're going to use symbols that mean a negative digit, but it doesn't actually. There are bases like that that do, like balanced ternary and stuff, where you have a symbol that means -1. But this is different. This is going to mean, okay, well, my powers are going to be powers of -2 or negative something else. And the ways we're going to mildly edit it here is, what if I say I'm looking at all bases whose absolute value, which is their distance from 0 or essentially makes their sign positive, is at least 2. And I'm going to use digits from 0 to 1 less than the absolute value. So if I did base -2, that works because its absolute value is at least 2. We could use the digits between 0 and 1, which is 1 less than the absolute value. And believe it or not, using the digits 0 and 1, I can use a base -2. And basically in the video I'm about to drop as soon as I end this stream, we use base 2 as a launching off point to then see base -10 and other options. And they surprisingly, although I will give the disclaimer that it's not necessarily a recommendation to switch to these bases. They're going to be harder to do certain types of arithmetic, you'll see. But they have some superpowers that the positive bases don't. So I can imagine circumstances where they could be useful, or I could imagine an alien species who used them. So I think I'm going to log off pretty soon because I want to launch that episode, but I'll probably do it until this stream is almost at an hour. And maybe if we're lucky later, it could be the day where I try and film something out of cutting into the cactus fruit, which, like I said last time, it doesn't look as fully ripe as it could be to me, but it fell off the cactus. So I think there's a decent chance that it's ready. Now, I have it in this thing because those little spines on the edge that look hairy almost are like splinters, and they're deadly. They won't injure you, but they will give you a mild, annoying, hard to remove injury for days. It's like splinters. So they will injure you just in a really mild and more annoying way, but it's like a bunch of little splinters if you touch one of those. So bad. But it's defense mechanism, as we've discussed. Now, when you cut into it, I need to look into this, but I don't think I'm supposed to eat the seeds. I think they're super hard. But eating around the seeds, there's an interesting flavor when I've tried them before. And the insides come in many different colors. I think this one might be more whitish or reddish, but I'm not positive. We'll have to see. So I don't have my supplies to do that now because I think I need to wear gloves to do it or something. I really don't want what happened last time to happen this time, where I got all these little micro splinters. So in any case, I think I'm going to wrap up in a sec. For all we know, I may have more stuff later, more short videos, or even another stream. You never know, because this stream was kind of more like a little math lesson where I wanted to, for one, investigate how to find some primes a little further in the number line, and for two, give a little sneak preview of the episode we are about to jump into. But thank you all so much for joining me. Sorry I didn't answer as many comments on this stream, but I still really appreciate them. Stay tuned right now, because as soon as I end this stream, I'm going to post the video on the other channel, on the main channel, which I'll put the link in right here. So anyone can feel free to click off the stream and over here now if you want. And it'll take me a second to switch accounts to that to do it. But as soon as the stream's done, it should be out within 5 minutes from then. So thank you all so much for joining me. I love you all. Have a wonderful day, and make sure to catch that new episode.